Hello everyone, this is Saurabh Joshi. I'm a principal researcher with Sopra research team, and today I'm going to talk about distributed oracle agreement. We at Sopra research have developed a new distributed oracle agreement, which we call DORA. So let's start. What are oracles? Well, oracles are people which looks into a crystal ball and tell you about your future. I'm just kidding. So oracle are actually mechanism which takes information from outside the blockchain. It could be maybe some another chain, or it could be some off-chain environment, and put that information in the blockchain. So why are oracles needed? So most of the blockchain or smart contract are isolated. So typically a blockchain is actually a sequence of state transition. And the sequence comes as a result of execution of a deterministic state machine. This determinism is crucial for blockchain. Now, let's say that if the blockchain needs to get some input, let's say, temperature of San Francisco, how do you do that? Because if there is an instruction in the state machine that read the temperature of San Francisco, different machines executing at different speed at different time may get different results. So you have non-determinism right there. So that is one challenge. Now let's say that we overcome that challenge by bringing specificity, by saying that, okay, tell me the temperature by sensor number 243 at San Francisco at time 12:03 p.m. on 22nd November 2022. But now the problem is that if 1 year from now, some machine is trying to execute this deterministic state machine, are they going to get the same result? For that to happen, you require a very reliable and immutable archive available so that every time you ask for the specific information, you get back the same result. Now, one mechanism that we know that allows archival in a reliable and immutable fashion is blockchain itself. And that's where the oracles come in. So Oracle takes away this divergence by taking data from various sources. It converges, and then it brings the specificity. It says that, okay, I, so and so Oracle service, certify that temperature of San Francisco City is so and so at this time. And then it puts it as part of the blockchain. So that means that now any node, even 1 year from now when it executes, you have that information available in a reliable manner right there. So that's why the oracles are needed. It bridges the gap between the off-chain world and brings that information to the chain. So let's start with the oracle design organization at Supra. So tribes are set of nodes, and this tribe of nodes we divide into a smaller set of nodes, which we call clans. So all clans are mutually exclusive and they are drawn from tribe randomly. Now we choose the size of the tribe and clan such that, assuming that tribe has about 1/3 Byzantine nodes, the probability that a clan has a Byzantine majority is negligible. And once we are able to divide tribes into clans in this fashion, what we do is that each clan is given responsibility to track different variables. In this particular case, let's say there are various cryptocurrencies like, Ethereum and Bitcoin and Polygon, etc. And different clans are given responsibility to track these variables and get information about those variables from various exchanges and then put that into the blockchain. So you can see that in this organization, we are able to do the sharding for the price pairs because we have the ability to divide the set into clans. Let's start with Bitcoin to USD price. So we have bunch of data sources. It could be various exchanges, various places, and our Oracle nodes, in particular clan nodes. What they do is that they get the information from this data source. So this mapping between a node and data source is very crucial. So imagine that if there is a one-to-one mapping between a data source and a node, in that case, what can happen is that if the node is Byzantine And if the data source is only feeding the information to only that node, then that information could be lost. And that's why it's crucial that one data source is feeding to multiple nodes. Now, similarly, we do not even assume that all the data sources could be reliable. Maybe some of them could crash, some of them may get technical glitch, or in general, they can be Byzantine. And that's why it's important that even for a node, the node has to listen to multiple data sources. So at Supra, what we mandate is that this mapping between data source to the nodes is done by a verifiable random function. So once a node has obtained data from various data sources, so let's say that it has obtained data from 5 data sources, assuming that we want to be able to tolerate failure of 2 data sources, that means that we should try to listen to 5 data sources. And then what we do is that we compute a median. Why median? Because median is a robust way to statistically aggregate a data where as long as the data corruption is less than 50%, it's not going to affect median. Now bear in mind that to tolerate failure of 2 data sources, it's okay to listen to only 5 data sources when we assume that the connection between the data source and node is most of the time reliable. If we want to have asynchrony assumption of communication between data source and node, then we require to listen to 7 data sources. So 5 is needed if our assumption is synchronous, and that's what we assume here, that from data source to node, the communication is bounded synchronous. So once every node computes their median, what they send is that they send to a bunch of aggregators. So we draw a family of aggregators from a tribe so as to ensure that there is at least one honest aggregator. So they're reading their medians, they send to all of the aggregators, these clan nodes. Now, once these values are at the aggregator does the following. Our clan size is, let's say, just for example over here is 30. So the aggregator waits till it can form a coherent cluster of at least 7 values. So what do I mean by coherent cluster? We define a parameter called agreement distance. And we say that 2 values agree with each other if they are at most agreement distance away from each other. So as you can see over here that all of these values, the distance between them is at most 4. So these 7 values form a coherent cluster. Now, these coherent cluster need not be unique. It's possible that from the set of value, you can form a multiple coherent cluster. For an aggregator, it's sufficient to form only one coherent cluster of one more value more than 50% so that you can ensure that there is at least one honest value inside this cluster. Now, sometimes it's possible that you are not able to form cluster. So as you can see that maybe some of these values, they do not form a cluster within the distance of 4 because the distance between some of these values is 8. So let's say that in a happy case, when you are able to form a cluster of size 7 when the clan size is 30, we know that in the worst case, when there are up to 6 nodes are Byzantine, there is still one honest value. And that honest value is going to act as an anchor. And you know that all the other values cannot be more than agreement distance away from this value. And that's why what we do is that after we form this cluster, the aggregator computes the arithmetic mean or the average of these values. Why average? Because now we know that there is an honest anchor and all other values are within agreement distance. We want the value of this particular honest node. There could be 1, there could be more. In the worst case, there will still be 1. And we want the honest value to be counted. So once the aggregator has computed the mean, it sends back for approval to all the clan nodes. It sends back the cluster, it sends back the arithmetic mean. Now, these clan nodes, what they do is that they validate that whether the cluster is indeed coming from the values of the clan nodes, whether they indeed form a cluster within the agreement distance, and whether the mean that is computed by the aggregator is indeed the mean of the cluster that has been set. As long as we have more than half of the votes sent back to the aggregator, it's good enough for forming a quorum certificate. And once this quorum is reached, the aggregator sends this value to SMR. So we use SMR as a black box and as an ordering primitive. And that is what is allowing us to have multi-aggregator model, because now SMR is an ordering primitive, which ensures that for any message sent to the SMR, there is going to be total order, and everybody is going to see the exact same total order. And that means that whenever there is a tie in this multi-aggregator one, we say that the first value that got posted to SMR is the authoritative value coming out of the oracle. Now, it's possible that we are not able to form a coherent cluster. None of the aggregator is able to form a coherent cluster within the agreement distance. Now, this is possible because if there is a extremely high volatility that even within the observation window, the window in which the nodes are obtaining data from data sources, in that window, if the values are differing very wildly, we may not be able to form a coherent cluster. So what do we do then? So what we do is that in such a case, we initiate a fallback protocol. So the way it is decided is that every node starts a timer after it sends their median value to the aggregator. And once they start timing out, they know that none of the aggregator has been able to post anything on SMR. So they send a vote for fallback to all the aggregators. If any of one aggregator is able to receive FC plus 1 votes, which is one more than half of the clan size, it posts the fallback message or the timeout message to SMR. This message would be seen by everyone, and then everyone decides to fall back. So what happens in fallback? So the moment the fallback message is posted on SMR, we shift the responsibility to compute this value, S value, from the clan to the entire tribe, because we know that we are in a zone where we can't form a coherent cluster. The prices are very wild. So we engage the entire tribe. Now the fallback protocol engages similar mechanism that we have seen earlier. So all the nodes gather their data from data sources. They compute their median. They send to the aggregators. But now you see that the tribe size is 3FT plus 1, where FT denotes that what is the maximum amount of faults or Byzantine faults tribe can tolerate. So now the aggregator, instead of waiting to form a coherent cluster, the aggregator waits to obtain responses from 2FT plus 1 nodes. Since only FT can be Byzantine, we know that at least FT plus 1 of them definitely be honest. And then we compute median because we know that median can resist corruption up to slightly less than 50%. And this median is sent to the approval of tribe nodes. The tribe nodes verify that the values are indeed signed by the nodes. The median is indeed the median of the 2FT plus 1 size set, and then they send their approval votes. And once there is 2FT plus 1 approved votes, the aggregator sends the value to the SMR. Now, why do we require fallback? So in times where the volatility is so high that even within the narrow window in which the data is being gathered from various data sources, you are not able to form a coherent cluster, we know that something is off. So maybe the clan size may not be enough. let's consult a larger body, which is the entire tribe, and the entire tribe is now engaged. So, in the times of these uncertainties, the tribe level consensus mechanism and this fallback provides a very safer and reliable alternative. Now, one thing to note is that in this entire protocol, one round of aggregation and posting to SMR does not depend on any of the previous round. And that means that you can start one round before waiting to finish another round. So that means that what we propose over here is a tick start DORA. So a tick could be, let's say, every few seconds, and at every tick, all the nodes are going to start yet another round of Oracle agreement. So you can see that, let's say that, there are 4 rounds. Imagine that round 1 starts, and even before the round 1 has finished, you can start round 2. Now, let's say that it's possible that, okay, they still happen sequentially over here. They don't have to. Now the round 2, so here, let's say S2 got posted on SMR, whereas the round 3 is on its way. Now, because of network latencies, asynchrony, or various other reasons, it's possible that now round 3 is taking longer. But you again still, start round 4. And if the round 4 starts and finishes earlier than round 3, we can just kill round 3 because now we have a fresh value available right here on SMR. And since we already have a fresh authoritative value on SMR, there is no reason to continue with round 3. So additionally, in our mechanism, we have various randomization measure to mitigate adversaries' power. So we have seen earlier that there is this mapping between various price pairs or commodities to various clans. And this responsibility is rotated. So there is a random permutation between these price pairs in the class. And this responsibility is randomly permuted via VRM. So that if the adversary wants to try to affect any specific commodity, it can't do for a very long time. So this rotation happens at every cycle, and cycle can typically be, let's say, few tens of minutes. Similarly, the another mechanism that we propose is shuffling. So we know that from tribes, the clans are drawn, and this redrawing of clan happened at the end of every epoch, where epoch could be, 1 day or 2 days. The end of every epoch, complete reorganization and shuffling happens. So the constituents of the clans can completely change. So this is also yet another measure to reduce adversarial collusion if the collusions are forming, where you are not giving enough time for the nodes to collude and try to affect a commodity of its choice. Now, additionally, there could be various things that can be done once we have computed these values. So you can see that different price pairs or commodities, many times they exhibit certain invariants or correlation between them. So imagine that, let's say X is Bitcoin to USD price, Y is Bitcoin to Ethereum price, and Z is Ethereum USD price. It is easy to see that ideally X should exactly be equal to the multiplication of Y and Z. Obviously, in practice, you expect that it won't be exactly X minus Y, Z will not be exactly 0. It would be a very small number, ideally. So when we know that if this number is more than what it should be, something is wrong. So we plan to exploit these correlations that exist across different commodities for detection of anomalous behaviors. Now, even within a sequence of S values that is computed in each round, there are various ways to compute some sort of anomaly or abnormal behavior. One of the classic function that is used as a circuit breaker function, where you see that if the new value that is computed, if that value is more than certain percentage, where threshold is a parameter, this could be 10% or 20% typically. So if this deviation of the current value to the previous value is more than certain percentage, then you can freeze the trade, etc. Now, the one problem is that this threshold is fixed and it only takes into account the previous value. Now, this can be a little bit generalized with this function, which we call a history consistency check, in which case we check that whether the current value is within this envelope that is defined by this interval, where it is SR minus 1 is the value coming off of the previous round, CH is a constant parameter, and sigma H is the standard deviation of a recent history. Now, how long of a history to look for, that is also again a parameter. So this defines the interval, and we see that whether the current value SR, and whether it lies within this interval or not. Now, the crucial difference between the circuit breaker and this history consistency check is that this dynamically expands and narrows based on the trend. So if the value continues to rise drastically for a very long period of time, we don't consider it as an anomaly anymore because the sigma would automatically expand this interval. So this has this added mechanism of dynamically adjusting the interval. Now, not only this particular function, once you have this sequence of values, we can use many other functions to detect anomalous behavior or abnormal behavior in the sequence. If it is done as off-chain, we can use even if computationally expensive statistical test. But if we want to include it as part of smart contract, it's good to choose a test which is computationally very easy to do, computationally less expensive. So we have seen that this entire design, organization, and the protocol is very decentralized with very high number of nodes between tribes and clans and very highly randomized, where the mapping between the data source to the nodes are randomized. The mapping of the price pairs that one wishes to track and the clan is randomized. And also the node to clan mapping is randomized. We have rotation, we have shuffle. So that does not allow an adversary to form a very long drawn strategy because the time is very short for any strategy to be very successful. And this we use as a mechanism to mitigate adversarial power. Not only that, it's very efficient because now we can shard executions for various price pairs across clans. And also it's very highly resilient because whenever we detect these anomalies, protocol switches to fallback protocol where more nodes are engaged. That's why it would be more reliable. Thank you very much for listening to this talk.